So in this screencast, we take ourselves all the way back to pictures like this from the Cinderella program, and we ask ourselves in the Cinderella program, how on earth did Cinderella know what to do? You'll remember that this is a disk centered at the origin. Usually it's of radius 1, but that radius is irrelevant. It's the disk, so it doesn't include the boundary circle. And we did things in the disk, and the disk represented the entire plane. And so we sort of accepted that it worked. We don't have to accept that it works. We can rigorously prove that this works. So let's just remember the axioms of neutral geometry. The axioms of neutral geometry say that there have to be more than one point in the set, and sure enough, that disk contains more than one point in the set. Then we had to show that between any 2 points, there exists a unique line, that between points A and B, there exists a unique line. Well, guess what? This line right here is an arc of a circle that is orthogonal to the boundary circle at its 2 points of intersection. And sure enough, we have proven that, well, it certainly can be proven that given 2 points A and B, there is a unique circle that is orthogonal to the boundary circle at the points of intersection. So existence is easy to check. Incidence also check. Okay, yeah, you're saying. But what about this one? What about the ruler postulate? We've got to show that there is a distance between A and B, and that distance can be any real number. Well, let's call this intersection point P and this intersection point Q, and let's define the distance AB as the absolute value of the natural log of AP times BQ over AQ times BP. Well, what do we want? We want, if A and B are really close together, we want the distance to be really close to 0. If A and B are really close together, then AP and BP are basically the same. AQ and BQ are basically the same. This is close to the natural log of 1, and the natural log of 1 is 0. If A and B are very far apart, then A is very close to P and B is very close to Q. And so this fraction is very, very close to 0. And the closer this fraction gets to 0, the closer its natural log gets to negative infinity, which can then be turned around every now and then. I get a little bit, right? So AB can be any real number between 0 and infinity, and that's what we need. Every line is, in fact, a number line. Angles. Oh, we don't do protractor yet. We do plane separation. Golly gee. Plane separation has to be a thing, right? Every line has to divide the plane into two convex, non-empty half planes. Well, that's yes, like that's true. Angles. How are we going to deal with angles? Well, we deal with angles the same way we'd always deal with angles, right? If two lines come together, these two lines, there are no lines in the picture that come together. So we imagine that there's another line that comes through, and and intersects line AB, and I want to know what that angle measure is. Well, Cinderella would find the tangent here and the tangent here and compute the angle between those tangents. Protractor postulate's going to work out just fine. No angles bigger than 180, obviously. 0-degree angles, obviously. Things are straightforward here. So then sixth axiom would be side angle side, but we've already ominously decided that we can go with the reflection postulate instead. But what does the reflection postulate look like in the Cinderella program? It's Euclidean inversion. It's Euclidean inversion in this boundary circle. What does that do? Points on the inside go to the outside, points on the outside go to the inside. Oh golly, I've so misspoken. Golly, when we reflect over AB, we do a Euclidean inversion in this circle. All of the points inside the orthogonal circle go to the points outside the orthogonal circle and vice versa. So Euclidean inversions do the job for us the way we want them to do the job for us. Remember that we only postulated 4 things. If you're on the circle, then you don't go anywhere. If you're on one half plane, you end up in the other. Distances are preserved, things like that. So Euclidean inversions accomplish for us in the hyperbolic plane what reflections accomplish for us in the standard Euclidean plane. So we have all 6 axioms established in the Cinderella program, and that's why Poincare's model, which is what the Cinderella program really does, Poincare's model for the hyperbolic plane holds. Everything that we can do in Poincare's model, we can do in hyperbolic geometry. What does that mean? It means that Poincare's model is consistent. We have a model for his geometry. So hyperbolic geometry is a thing. It really exists. It can be modeled. The fact that the model is Euclidean does not mean that hyperbolic geometry is Euclidean. It means that we use a Euclidean plane to model some other plane that is very clearly not Euclidean. So that's how Cinderella works. That's the whole math behind why they do what they do. I hope it is somewhat enlightening, takes us all the way back to the beginning of the course, adds in all the stuff that we figured out at the end. Sincere best wishes as we wrap things up.